Hello and welcome back to Basic Topology, the video series where we talk about open sets, closed sets and compact sets. And in today's part 2, we give the definition of a topology and a topological space. And moreover, we will see that this is the generalization of a metric space as we want it. However, as always, before we start with these important definitions, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, you can just click the link in the description to download additional material for the video. And then without further ado, I can give you the overall idea of topology, where we just consider a set X. And such a plain set we want to equip with more structure, and this will be the topology. And this works by just looking at the whole collection of subsets of the set X. Taking subsets makes sense because they give us a classification for neighboring points. And the special subsets we choose are just called open sets. So this is different from what we know from metric spaces, because now these open sets are the starting point of the definition. So we take any set X and then we look at the power set of X. This one is usually denoted by P of X and consists of all subsets of X. And now what we do is to take a subset of this power set, so we just take a collection of subsets. And usually we denote that by a curve T, and there you should remember that the elements of T are subsets of X. So this new set consisting of subsets is called a topology on X if three properties are satisfied. And in fact we already know what they are because we have discussed these properties in the first part. First, the empty set and the set X itself have to lie in this collection. So this implies that a topology is never equal to the empty set, but it always contains the empty set as an element. So this is important to remember. We have these two subsets as an element in T. And now the second property is quite simple. Whenever you have two elements from T, then the intersection of these two subsets is also an element in T. And by just applying this property again and again, you can already remember that finitely many intersections stay in T. And this is in contrast to the third property, where such a finite restriction is not needed. There you can take as many subsets as you want, and let's call them AI. This means this index set capital I can even be uncountable. And then the implication is that the union of all these subsets still lies in T. So in short, a topology is closed under forming unions, under forming finite intersections, and it has the empty set and X as elements. And at this point you already know that these special subsets is what we call open sets. Hence in that context, saying open just means it's an element of T. And with that, we have the whole structure, which means the set X together with all these open sets. And this is exactly what we call a topological space. So you see, on a given set X, different topologies are definitely possible. And different topologies will lead to different topological spaces, which could behave completely differently. And as you might already know, we will study a lot of different ones in this video course here. However, you should never forget about the most important one, which is just our standard Rn. In fact, Rn is a topological space simply because we have our standard Euclidean norm, which measures the length of a vector x. So this is the definition of the Euclidean norm, and what you should understand here is that such a norm is just much more than just a topology. Indeed, what happens here is a simple line of thoughts, because we immediately get a metric from a norm. This works in any vector space with a norm, because we can just measure the length of the distance vector. And now whenever we have a metric, we know by the first video that this induces a topology as well. The only thing we have to do here is to take the old notion of open. Hence the set A here is open with respect to the metric D. And how this works you already know from the last video. We just have to take the epsilon balls in Rn. This means for every point in A, we find an epsilon ball around this point that lies completely in A. And from the last video, you already know this is the short formula for that. And there you see we have the epsilon balls, and you might know that the form of the epsilon balls depends on the chosen norm. Therefore, with a different norm on Rn, the balls could look completely different. However, the thing here is that the notion open will not change with the looks of the balls. This means if you choose a different norm on Rn, everything here will be different except the topology in the end. This is a nice result because it tells us that this standard topology we have on Rn is quite fundamental. Namely, this topology just comes from any norm on Rn. But of course, it's not the only topology we could choose on the set Rn because we don't have to start with a norm at all. This means we always have to say which topology we mean, and only if we don't say anything, we could assume that we mean the standard topology like that. So for example, a topology that always exists is the so-called indiscrete one. In this one, only two sets are open, namely the empty set and the set itself. This is a really rough topology because it essentially means that any point is close to any other point. In fact, I would say this is quite clear when we look at convergence sequences in the topological space. However, I don't want to do that right now because first I also want to talk about closed sets and compact sets. We already know these concepts for the standard topology or for metric spaces, and now we want to generalize them as we did it for the open sets. And maybe here as a remark, this indiscrete topology does not come from a metric at all, but we could definitely have a metric that induces a topology which is not equal to the standard topology. But as you might already know, this is something for the next video. So I really hope I meet you there again and have a nice day. Bye bye.